Hi everyone, I'm Mehdi Motamedi. I'm a software engineer and system programmer, and today I'm going to walk you through how Linux schedules processes and threads. This is a fundamental topic for understanding Linux performance and responsiveness, especially in multi-core, real-time or server environments. We'll cover several core aspects of Linux scheduling. First, I'll introduce the main types of schedulers available in the Linux kernel. Then we'll look at how Linux handles processes priorities using Niceness. After that, I'll go over how Linux balances tasks across multiple CPUs and how you can influence task placement using Affinity. We'll discuss Preemption, both at user level and inside the kernel, and how it affects latency. And we'll wrap up with how to tune the scheduler for specific performance goals. Scheduling in Linux determines which process gets access to the CPU and for how long. This is critical for performance, fairness, and responsiveness. Linux uses preemptive multitasking, meaning it can pause a process even if it's not done, in order to switch to another task that may be more urgent. The goal is to keep all system resources utilized effectively, while also avoiding starvation or bottlenecks. The scheduler uses algorithms that factor in process priority, task type, and sometimes even deadlines to decide which process run next. The Completely Fair Scheduler, or CFS, is the default and works well for general purpose workloads. CFS is designed to ensure fairness. All processes get CPU time proportionally to their priority. It uses a data structure called a red-black tree, where each process is stored by how much CPU time it has already received. Processes that have had less CPU time are moved to the front. CFS constantly calculates virtual runtime for each task to track fairness. This ensures no process is starved and time sharing is smooth. There are real-time schedulers for time-sensitive tasks. For tasks that require predictable timing, like audio processing or robotics, Linux supports two real-time policies. Sched FIFO, first in, first out. Tasks run until they block or get preempted by a higher priority real-time task. There is no time slicing. Sched RR, round robin. Similar to FIFO, but includes time slices. Once a task's time slice expires, it's pushed to the back of the queue. Real-time tasks always take priority over normal processes, so misuse can starve the system if not managed carefully. There is also batch and idle scheduling for low priority or background jobs. Sched batch is ideal for CPU-intensive background tasks that don't need immediate interactivity. These jobs get longer CPU bursts and are less likely to interrupt interactive tasks. Examples might be video encoding or data processing jobs running in the background. Since they don't interfere with user interaction, they help optimize overall system performance. Sched idle is the lowest priority policy. Tasks using this only run when no other tasks need the CPU. It's useful for things like indexers or periodic background analysis that can wait indefinitely and shouldn't interfere with other work. Linux uses priorities to determine who runs first. There are two types. Static priorities are for real-time tasks ranging from 0 lowest to 99 highest. Dynamic priorities are for normal tasks and influenced by the nice value. Nice values go from -20 to +19. A process with -20 runs as high priority and a process with +19 runs as low priority. This lets users or admins lower the priority of background tasks so they don't interfere with more important ones. In multi-core systems, Linux tries to keep CPUs equally busy. It moves tasks between CPUs to prevent some cores from getting overloaded. But you can pin a process to specific CPUs using CPU Affinity. This is useful for performance tuning. For example, isolating latency sensitive tasks on a dedicated core. You can control this from user space with the task set tool or programmatically using a sched set affinity. Preemption allows Linux to interrupt a task to switch to a more important one. There are different types. Voluntary preemption happens when a process blocks an I/O or calls a sched yield. Involuntary preemption happens when the scheduler forcibly switches to a higher priority task. Kernel preemption means the kernel itself can be interrupted, depending on the configuration. This improves responsiveness but can increase complexity in synchronization. The kernel can be compiled in different preemption modes. Config preempt voluntary. Tasks yield only at certain safe points. Config preempt enables more frequent preemption within the kernel for better responsiveness. Config preempt RT. With the real-time patch, the kernel can be preempted almost everywhere, making Linux suitable for real-time applications like telecom or robotics. You can fine-tune the Linux scheduler using syscall settings. Two key parameters are sched latency NS. Target time between process switches. Larger values favor throughput. Smaller values favor interactivity. Sched min granularity NS. The smallest time slice a process can get. Tuning this helps optimize performance for your specific workload. For example, gaming server or HPC environments. Thanks for your attention. I hope this helped clarify how Linux scheduling works and what tools are available to manage it. If you have any questions or want to discuss specific scenarios, feel free to reach out.